Have you ever noticed sparks when you disconnect an electric motor or a relay from a power source? That sudden flash of energy is more than just a visual spectacle. It is a sign of potentially damaging voltage spikes at play, an unseen force that can wreak havoc on your sensitive electronic circuits and components. Understanding this phenomenon is key to designing robust and reliable systems. A flyback diode, also commonly known as a freewheeling diode or a snubber diode, suppresses back EMF by providing a safe, alternative path for the current generated by an inductive load when the power supply is suddenly interrupted. This redirects the stored energy, preventing large, damaging voltage spikes from occurring across the switching element. The core principle behind this phenomenon lies in an inductor's fundamental property, its opposition to changes in current, governed by Lenz's law. When current flows through an inductor, like the coil of a relay or a motor winding, it stores energy in a magnetic field. If this current path is suddenly opened, the magnetic field rapidly collapses. To maintain current flow, the inductor induces a very high voltage in the opposite direction of the original supply voltage, often referred to as back EMF or inductive kickback. Without a flyback diode, this voltage can momentarily reach hundreds or even thousands of volts, easily exceeding the breakdown voltage of a switching transistor and causing it to fail. To implement this protection, the flyback diode is connected in parallel with the inductive load. It is placed in a reverse-biased orientation, meaning its cathode connects to the positive side of the power supply and its anode connects to the negative side. While the main circuit is on and current is flowing through the inductor, the diode is effectively an open circuit and does nothing. However, the moment the power supply to the inductor is switched off, the back EMF generated causes the voltage across the inductor to reverse polarity. This forward biases the flyback diode, allowing the inductor's current to circulate safely through the diode and the inductor itself, rather than flowing back to the switch. This elegant solution mitigates a common issue known as inductive kickback, which is a significant source of electromagnetic interference, or EMI, by offering a low-resistance path for the inductive current. The diode allows the stored magnetic energy to dissipate gradually as heat within the inductor and the diode itself. This proactive measure not only safeguards your invaluable switching components, such as BJTs or MOSFETs, but also dramatically increases the overall reliability and lifespan of your entire circuit, especially when using microcontrollers that are highly susceptible to voltage transients. Ultimately, the strategic use of a flyback diode is a foundational technique in electrical engineering. It is an indispensable tool for anyone working with inductive loads, ensuring that the natural tendency of an inductor to resist current changes does not lead to destructive voltage spikes. This simple component is a powerful guardian, transforming potential circuit damage into a safe and controlled energy dissipation.